course, Intelligence Processing Unit, IPU. This is version 1. They have also released version 2. So first of all, this is the architecture. So it has lot of number of tiles. Okay, and each tile has its own local memory. So let us also open Cerebras. Okay, in Cerebras, let us compare it with Cerebras. Now Cerebras has so many. It has like 4 lakh cores. Now what was the architecture? So it has MIMD architecture. Okay. Memory is local. There is no shared memory, right? So this one also had a local memory, and it is like this. So here, this is 4 lakh cores. So you can call it core or you can call it P. So every core has its own local memory, SRAM memory. Okay. Similarly, here we are calling it a tile. Now each tile has its own core and its own local memory. So here also you can see the memory is local. So it's like a very, very distributed architecture. There is no sharing of memory. That means there is no single memory that is shared between the cores. Every core has its own memory. And here the size of memory is 256 KB. I think in here there was the memory size. Is it explained here? I forgot. The amount of memory which is there, that is not shown here, I guess. So probably we could divide this. See, I think we have 18 gigabyte of SRAM. 18 gigabyte of SRAM. So you can divide number of cores. Then you can find out how much memory is there in each core. Similarly, here they have already shown that every core has, every core gets access to 256 KB local memory. So again, they are scratchpad. By the word scratchpad, I mean just it is software managed memory. So almost all the accelerators we are seeing, they have software managed memory. They don't have hardware managed caches, and also there is no shared memory. So what is the example of shared memory? Okay. Yeah. So here, of course, so here we have this local memory, right? Every core has its own local memory, plus it also has a shared memory. So here, like we don't have that kind of shared memory. Okay, so memory is SRAM with 45 terabyte per second aggregate bandwidth, and it has 6 cycle latency. And here, memory bandwidth is 9 petabytes. Okay, so which one is higher? Which value is higher? Which one has more bandwidth? Cerebras or IPU? Any answers? See, but one of them has 45 TB per second, another one has 9 TB per second. Which one of them is higher? Anupam?
Sir, 9 PB is higher, sir.
9
PB beta would be higher, sir.
Yeah, you're right. Yeah, 9 petabyte is higher. So of course, as I said, so this is aggregate bandwidth, which means that if all the cores were accessing and they were accessing their local memory, then what is the maximum bandwidth you can achieve? Which assumes that all the cores are active. Now, of course, as I always say, this Cerebras is a very, very different scale altogether, right? It is not even a chip; it's a wafer. So nothing can compare. I mean, right? No chip can compare with a wafer. So IPU uses MIMD, similar to the approach of Cerebras that also uses MIMD. So the whole point is, see, we have so many cores, and each core can get its own instruction. It works on its own data. Okay. See, it's very, very difficult to give that. Okay, that all the cores, right? It has how many thousands of cores, right? 1200 cores. It's very difficult that all the 1200 cores will be executing the same instruction. That's why MIMD approach is better. Let them work on different instruction, they will be operating on different data. If working set fits in the local memory, there is no cost of control for divergence because each core accesses the local memory at a fixed cost independent of the access pattern. So that means if sometimes, like if you see in GPU, we discussed that branch divergence is a big issue, right? Because if some data misses, then you'll have some of the threads will have to go get the data from main memory. Some of the other threads, the data is available locally itself. So this creates an issue. Whereas here in IPU, it is more efficient than GPUs for applications with irregular memory access or control flow dominated applications. Control flow means that if else conditions, which conditions, or wherever you have branch conditions or jump conditions. Similarly, irregular memory accesses means like this. For example, you know, right, when we have pruned memory, then some of the threads will get data, some of the threads will not get data. So this will lead to irregular memory accesses. So for IPU, it is less of a concern because as long as you can get the data from local memory, it's not a problem. Whereas GPUs, they also have hardware managed cache. I mean, GPU also has a shared memory, which is software managed, but GPUs also have hardware managed memory, so that their irregular memory accesses will create a problem. So IPU also uses multi-threading. That means it uses so many threads. That means for every core we have, I think six threads. Yeah, 6 threads. So in Intel's hyper-threading, we have two threads on each core. Usually two threads can run. Here 6 threads can run. That means the resources of a core will be used by 6 threads. One of them may be stuck, one of them may be not used, but others can always use it. Okay, so the whole point is just like, you know, suppose I purchase a server, GPU server. Now, I mean, it's an analogy. It's not actually, it's an analogy. Like now, I want it to be optimally utilized. So I will give access to 5 students. Okay, you use the GPU. So even if one person is not using, at least other person is using. So my money that I invested should not go waste. That's like oversubscribing. Ideally, only one person should work on each GPU, right? So that he can get, but we are oversubscribing. So this hides the execution, instruction execution latency, because even if one thread is stuck, you can switch to another thread. That's the whole idea of multi-threading. Okay, we discussed this point in the GPU. That if one thread is stuck, you can move to the next thread, and if that is stuck, you can move to the next thread. So in that way, you don't have to wait for the memory access. Now each tile rotates among threads according to a static round-robin schedule. So that means the scheduling between the thread is in a round-robin manner. And it's a static. That means it's a fixed order. Okay, it's a fixed order. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so each tile has accumulating matrix product unit, which is similar to GPU's tensor core units. Okay, so it accelerates matrix multiplication and convolution. So in Hanguang also we saw that it accelerates both matrix multiplication and convolution. Although you can always, you know, convert convolution into matrix multiplication, but you should be able to also directly accelerate convolution. So that also ability it has, similar to Hanguang. So an EMP can finish 64 mixed precision or 16 single precision flops per clock cycle. So let us compare it with tensor core. Okay, so here, okay, so in each cycle, tensor core can perform 64 FMA operations. Okay, of course, they are all mixed precision, right? They are half precision. So here it is 64 floating point FMA operations. So here, how many can it do? It can also do 64 mixed precision flops, but here it is flops. There it was mag. Okay, we'll see, but we'll see more. Yeah, here. So Okay, this is 124. Theoretically, it has 124.5. Whatever. This is gigaflop, right? What is the unit here? Teraflops. Just a minute. So there it was 125 in GPU. Here it was 125 teraflops per second, right? So because it has 6640 tensor cores, has a theoretical 125. So here, now let us compare. So here it has 640 tensor cores. Okay, and here we have double. If you multiply 640 with 2, how much you get? Almost double, right? So it has more, it has double the number of tiles. Okay, it has double the number of tiles. However, the difference is that here we are talking about 64 FMA operations. Okay, and FMA equals to 2 operations. Okay, FMA equals to 2 operations. Whereas in here it only performs 64 flops. It doesn't say 64 FMA operations. Okay, is it clear? So that's why now if you try to compute the performance, yeah, I'm trying to see here it is. So this is for tensor core. Now let me compare it for the. So here it is 12.16. Instead of 1.53 clock, the clock here is 1.6 hertz, and this one is gone because it doesn't do. So this one is for IPU. Okay, so this is 12.16 into 1.6 gigahertz. That gigawatt is coming here 10⁹, and it can do 64 floating point operations in each cycle. So now, can you tell me what is the peak performance here? Please do. Somebody can do the math. Tell me the number. Tell me the answer to this. In terms of teraflops per second, what is this number? Anyone, please? No one?
Sir, it is coming around 1.24 petaflops into 10 to the power 15, sir.
1.2 10 is to no. You just compute this value.
Okay, sir.
Just compute this value. Forget everything else.
It's coming 1,23,194.
Just a minute. So let me write down this. So how much is this value?
So it is 1,23,494.
294. This much?
Right, the 494. Last one is 494.
Okay. Very good. Okay. So now, this is in terms of gigaflop, because this 10⁹ is gigaflop. And now if you want to convert into teraflops, then you make it. Sorry. This is teraflop. Is it fine, everybody? This was 10⁹ and teraflop is 10⁹12. So I moved the numbers. So now you see it is almost same. It is 125 here. Here it is 124 almost. So that's what this number. This 124.5. That is maybe some. It may not be exactly 1.6. It may be like 1.6 something gigahertz. Okay, that's why it is not exactly 123. It is 124, but that's very minor difference. So in single in double in mixed precision, it will give 124 teraflops per second, which is very close to what a tensor core can give you. Not a single tensor core, but 640 tensor cores. That means all the tensor cores put together on this Volta V100 GPU. So that means this is matching. Now, if you see the vector, that means single precision. This was for the mixed precision. And here, if you see the vector, but for the single precision, here it is 31. Now, tensor cores can't do single precision. Tensor cores can only do mixed precision. But here, this FP cores are the CUDA cores. Okay, so FP cores are here. You see here, it also has 30. This FP32 cores. Okay, 5120 FP32 cores. That's what we are comparing here. So this FP cores is the performance of those 5120 cores. So compared to that, here it can do this much. So 31 versus 15. So this is a theoretical performance, and this is the actual performance that you obtain on matrix multiplication. So here it obtains only 58.9 teraflops per second, whereas GPU can obtain 90. Okay, that means it can achieve higher fraction of the peak performance. GPU has a better utilization than IPU. Is it fine, everybody? It is clear. So although the peak performance of IPU is matching compared to the P100 compared to the tensor cores in P100 GPU, but when you actually run it, that because of availability of memory or whatever reasons, you are not able to fully get the entire performance. You get only less than half, whereas here you achieve 72%. Okay. So another thing is IPU does not support double precision, and that is not even required, right? In deep learning, we have not seen any accelerator which supports double precision. So I have explicitly mentioned it, but we never bothered about double precision. We only bothered about single precision, half precision, and so on. Okay. So although I mentioned it, but don't think it's a big red signal. It is just for sake of completeness I mentioned it. Okay. So from this, so that means it has EMP units and it also has vector units. That's why there are two performances that are shown. So that vector unit is not mentioned, it's not written here, but it's clear that it has EMP units also and it has vector units also. Both units are there. Okay. So now, so I already just now mentioned that for the mixed precision, IPU processor matches the performance of P100 GPU. Whereas for single precision, one IPU processor offers 2x the theoretical peak throughput compared to one P100 GPU. So here, 31 versus 15. Because here we can't use tensor core. Tensor core can only do mixed precision, whereas EMP can do both single precision and mixed precision. So here, this is 31, this is 15. Although the percentage of peak that you can utilize here is only 60% compared to 98% here. So here, you can see the CUDA cores are really quite efficient. You can use almost the full performance. Okay, so this kind of magic, compare and contrast, you should always be able to do. So now immediately you understand. Okay, you are boasting of having so many resources, but you're not able to use a lot of them, right? So that means it's not just sufficient to design a fancy hardware. You should be able to, utilize. You should be able to utilize that hardware. So now IPU delivers higher throughput. So I think that is for this. Here does it offer? So here, that is for this one. Of course, the theoretical throughput is higher and actual throughput is also higher. Only the percentage of the peak that you are able to achieve, that is lower. GPU supports larger operand thanks to its high device memory capacity. Now, one thing is, where is the DRAM? So what do you think? What do you think about the DRAM? Where is the DRAM here? Do you see any slot for that, or where is the DRAM here? Any thoughts?
It should be off chip, sir.
No, DRAM is off chip. Yes, I know DRAM is always off chip. But where will you plug it? Where will you plug it? Do you see any port? I mean, see IPU link is what? See, this IPU link is that if you want to connect one IPU with another IPU, so for that you need this IPU link. Okay, so all you have left is this PCI. So can you connect DRAM with PCI link? Have you seen any accelerator where they're connected? Yes, Sagar.
Yes, sir.
Have you seen any accelerator? I mean, in my course, where we have connected DRAM on PCI Express bus. Okay, but okay, let me answer. See, this PCI is for connecting this to the host. So at least the version 1 has there is no DRAM here. All it has is SRAM. Fine, just like Han Buang, just like Cerebras, there is no port for DRAM here. Although in version 2, they have introduced that it can have DRAM backup also.
Grayscale, sir.
Grayscale is another example where they don't have. No. Grayscale has DRAM. Grayscale has DRAM, right? So let us compare that. I'll show you where is the port for that in Grayscale. So you should be able to observe all this. Okay, so here, see here you connect the DRAM here, but it has the controller here. Okay, that is also mentioned somewhere. Yeah. No, word of, but okay. So this PCI Express slot that is for connecting to the host. Always remember this. PCI Express is for connecting to the host, and for DRAM, this we have not written in the text here. I was trying to look whether we have. Yeah, here, okay. 8 DRAM controllers. Yeah, that's the point. NOC also connects to, so this network on chip connects to 8 DRAM controllers. So these DRAM controllers are this. So here, what you see as LPDDR4, that is a DRAM controller, and DRAM memory controller is always on chip. So I will also show you that design. I think it is here. Yeah, here, okay. So this is the memory controller. So this is a CPU. This is a 4-core CPU. So this is the DRAM memory controller. This is the DRAM interface. Now memory controller is always on. This memory controller is on chip. Okay, so that's what you have to look for. So here there is no DRAM controller. So that means it relies only on SRAM. So now because now GPU has DRAMs. That's why GPU can have higher memory, right? DRAM capacity is much higher. Okay, and one more thing is from this you can also compute what is the total amount of memory that is available here. If you multiply this number with this number, you can see what is the total memory that is available on IPU. So the largest, so this is based on their so someone has done this experiments on GPU and IPU. So they found out that the largest square matrix that fit one IPU is this size, whereas a 32 gigabyte GPU can fit even this much square matrix. Each IPU uses 150 watts of power. So that is its TDP is around that, and NVIDIA V100 has a TDP of 250 watts. Okay, now IPU's local memory is lower latency than the fastest memory on the Turing GPU. So let us see the comparison. So here Graphcore IPU. So this is memory style local. That means every tile has its own local memory. Per chip capacity 304 megabytes. So how do you get this number? Can anybody tell me? How do you get this number? Yes, Subham, Vikas. Suman? Anubha? How do you get this number? 304 megabytes. Okay, nobody is able to do. I'm surprised. This is very, very. Just now, 2 minutes before I said, if you, yes, you want to say something? Just now I spoke, right? If you multiply this with this, what do you get? You get 304 megabytes, isn't it? If you multiply this number with this number, you get 304 megabytes. Okay, so that is the total amount of memory that this IPU has. Fine. So the on-chip memory of IPU is just 304 megabytes. And how much on-chip memory was there on Hanguang? You discussed yesterday.
So 48 MB.
No, you have to do more math there.
384.
No. Okay, you are recollecting some individual numbers. So 384 KB was one module. And
So
48
192 MB.
Sorry?
192 MB.
Yeah, 190. So 48 MB was in the single core, and then there are 4 cores like that. So 192 MB. So compare that 192 MB with this 304 megabytes. Right? 192 there, and higher it is 304. Okay, good. So let us go forward. So here this is total is this is on the whole chip, Okay, so this is 304. Now the latency is 3.75 nanosecond, and given this frequency, if you convert it into latency, this comes out to be this. And one more thing, you can see this frequency anyway not very high. Okay, Hanguang had 700 megahertz. Here it is just that. Here it is 1600 megahertz. That means 1.6 gigahertz. So here latency is only 6. This is if you convert it into cycles. And here this is 19 to 32 cycles. That means here shared memory and L1 cache, they have much higher latency. Now because CPU is designed for minimizing the latency. So on CPU the latencies are very low. So that means the whole point is this latency compares with this latency. Right? This latency is like 5 cycles here. This is 6 cycles here. That is comparable. So that means Graphcore IPU local memory can be accessed very fast, just like L1 cache of CPU. Okay. Although local memory is vastly larger than those memories in the per chip comparison. So here it is like total 304 megabytes because it is distributed. Although total capacity is very large, each tile has only 256 KB. Okay, every tile gets access to, every core in the tile has access to 256 KB that you can easily access. Okay, so this is the whole point. So this is the total memory comparison. This is the site 304 megabytes, and here 300 total. This is 10 megabytes of L1 or shared memory. L2 memories, L2 cache is just 6 megabytes, and HBM2 it has, that is 16 gigabytes. Now on CPU Skylake with 2 sockets, each having 24 cores. L1 cache is 1.5 megabytes, L3 cache is 66 megabytes, this is 768 gigabytes. Now here you can see the total bandwidth is much higher, 12,420 gigabytes per second. Here it is 11,500. Here it is only 7,000. Okay. So now you can see the. So again, effectively you achieve high bandwidth, but still remember that this utilization, their utilization is low. So that means there may be some other issues. At least if you just see the raw numbers, without running any workload, if you just see okay how much resources they have, then it is very good. So software designers must partition the working set across the tiles memory appropriately and make tile exchange data with each other and reveal non-local options. That means, see, if every core in a tile needs to operate on more than 256 KB data, then that data has to be stored in some other tile, right? I mean, the local memory of some other tile. So you have to be able to efficiently move the data and supply it to the whichever core it needs, whichever core needs the data. So tile can exchange data using a very fast all-to-all on-chip interconnect. Okay, so if you remember in Han Guang, we had ring architecture. In Grayskull, we had a torus architecture. Okay, so here it is again all-to-all. So you can very quickly supply the data. Now we have one IPU which has 304 megabytes. Now one board has 2 IPUs. That's why total memory in a board becomes 608 megabytes. If a model requires more than this, it can be divided across multiple IPU processors or IPU boards. Just like we said in Han Guang, if you need more than 192 megabytes, you have to use multiple Han Guang chips. Similarly here also. This is the reference.